Standing in the shadow of an ancient stone house, you can't help but wonder, how did they do it? No steel beams, no cement trucks, not even a simple nail. Yet these structures have weathered centuries, standing strong long after many modern buildings have crumbled. That's the magic we're uncovering today. The incredible story of how people built homes with no modern tools. It's a tale of human ingenuity, where every beam, every stone, every woven wall was shaped by hand, guided by knowledge passed down through generations. These weren't just shelters, they were testaments to what's possible when creativity meets necessity. Think about the last time you assembled furniture with an instruction manual. Now imagine building an entire home without so much as a measuring tape. Our ancestors relied on observation, trial and error, and an intimate understanding of their environment. They turned trees into timber using stone axes, mixed mud and straw to make bricks stronger than concrete, and fitted stones so precisely that not even a blade of grass could slip between them. These techniques weren't just practical, they were art forms deeply tied to the cultures that perfected them. From the igloos of the Arctic to the thatched cottages of Europe, each design was a masterpiece of adaptation. But here's what's truly astonishing. These ancient methods hold lessons for us today. In a world grappling with climate change and dwindling resources, the sustainable wisdom of the past could light the way forward. How did they insulate homes without electricity, cool them without air conditioning, build communities without destroying the land? As we journey through the secrets of these timeless structures, you'll see history in a whole new light, not as a distant memory, but as a living blueprint for resilience. So let's step back in time together and discover how the humblest materials, shaped by human hands, created wonders that still leave us in awe. One of humanity's first great breakthroughs in construction was the post-and-lintel system, simple in concept but revolutionary in impact. Picture two sturdy upright stones with a massive slab laid across them, like a giant's table. That basic framework became the backbone of ancient architecture, appearing everywhere from the temples of Luxor to the stone circles of Europe. What made it so brilliant? It tapped into the raw power of compression. The vertical posts bore the weight, while the horizontal lintel distributed the load evenly, creating openings that could support unimaginable weight without collapsing. But here's where the real ingenuity shines. Ancient builders had to solve this puzzle without modern engineering. They couldn't rely on steel reinforcements or industrial adhesives. Instead, they studied the land like artisans. For the Egyptians, granite and limestone were chosen not just for strength, but for their ability to lock together under pressure. The Greeks took it further, tapering their columns slightly upward to create an optical illusion of height while actually improving stability. And at Stonehenge, those towering lintels weren't just dropped into place, they were carved with tongue and groove joints, a prehistoric version of Lego blocks, ensuring they'd stay put for millennia. This wasn't just about brute force, though. The post-and-lintel method reveals how deeply ancient builders understood their materials. Wooden versions, like those in Viking longhouses, flexed with the wind instead of resisting it, while stone iterations defied earthquakes by letting joints shift slightly. Every culture adapted the technique to their environment, proving that the best technology isn't always the most advanced, it's the one that listens to nature. Today, we still see echoes of this wisdom in everything from barns to bridges, a testament to the timeless power of balancing weight, trust, and patience. Now imagine a wall that breathes with the seasons, flexing against storms and trapping warmth in winter. This was the genius of Wattle and Daub. Unlike rigid stone or timber, this ancient technique embraced flexibility. Builders would weave slender branches, willow, hazel, or oak shoots into a lattice as tight as a basket. Then came the alchemy, a sticky mix of clay, mud, and straw, sometimes enriched with cow dung or animal hair, pressed into the gaps until the wall became solid yet supple. It wasn't just cheap and quick to build, it was alive, adjusting to humidity and temperature in ways modern materials still struggle to replicate. What's astonishing is how widespread this method was. From the round houses of Celtic Britain to the long houses of the Iroquois, cultures continents apart arrived at the same elegant solution. In Japan, a version called kominka used bamboo wattles and rice husk-infused clay, while in Africa, termite mound soil, naturally reinforced by insect saliva, created walls that could outlast concrete. The secret wasn't just in the materials but in the layers. Daub acted like ancient drywall, absorbing noise and moisture, while the wattle's weave distributed stress evenly, preventing cracks. And when repairs were needed, a handful of mud and straw was all it took. No demolition crews, no landfill waste. This wasn't just construction, it was collaboration with nature. The straw in Daub wasn't just filler, it acted like microscopic rebar, preventing shrinkage as the clay dried. Animal hair, often from horses or oxen, added tensile strength, mimicking the function of modern fiberglass. Even the choice of clay mattered. Builders would test soils by rolling them into ropes. If the coil cracked, the clay was too sandy. If it held, it became the glue holding entire villages together. Today, architects are rediscovering these principles, using hempcrete and rammed earth to build carbon-neutral homes. The lesson: sometimes the oldest solutions are the most advanced. Yet Wattle and Daub's greatest legacy might be its humility. These walls weren't meant to awe like pyramids or cathedrals. They sheltered families, stored harvests, and echoed with laughter. They remind us that great building isn't about dominating the landscape, but belonging to it. When a storm hit, these walls didn't resist the wind. They danced with it, bending just enough to stay standing. In an age of skyscrapers, that's a wisdom worth remembering. Strength doesn't always come from rigidity, but from knowing when to yield. Dry stone masonry might seem impossible at first glance. How could stacks of loose rocks hold together for centuries without a drop of mortar? Yet from the terraces of Peru to the sheepfolds of Scotland, this ancient technique defies logic. The secret lies in the art of selection. Builders didn't just pile random stones, they became geologists of necessity, handpicking rocks whose natural shapes interlocked like puzzle pieces. A flat face here, a slight curve there. Each stone was rotated, tested, and sometimes painstakingly reshaped with stone hammers until it found its perfect neighbor. The result: walls so tightly fitted that even now you can't slide a credit card between the seams at Machu Picchu. But this wasn't just about precision, it was physics mastered through observation. Without mortar, every stone had to bear its share of the load. Builders angled stones slightly inward as walls rose, creating a subtle curve that funneled weight downward, not outward. Earthquakes: these walls had a built-in defense. The absence of rigid mortar meant stones could shift slightly during tremors, then settle back into place like a self-healing mosaic. In the Andes, Inca engineers took it further, embedding trapezoidal doorways and tapered windows to redirect seismic forces away from weak points. What's truly humbling is the scale of patience required. Unlike modern construction, where cement sets in hours, dry stone masonry moved at the rhythm of the craftsman's hands. At Sacsayhuaman, the zigzagging walls contained stones weighing over 100 tons, each dragged for miles, then coaxed into alignment over years. No blueprints, no cranes, just trial and error, with generations often completing what their ancestors began. Today, we're rediscovering the brilliance of these methods. Dry stone walls require no mining for cement, emit no carbon, and outlast their modern counterparts by centuries. In Ireland, farmers still maintain walls built this way during the Bronze Age, proof that the strongest bond isn't always chemical but gravitational. As one modern stonemason put it, a well-built dry wall doesn't fight gravity, it collaborates with it. That's the timeless lesson etched into these silent stacks of stone. Sometimes the most enduring strength comes not from forcing nature, but from listening to it. Thatch roofing might look like a simple heap of straw from a distance, but up close, it reveals itself as one of history's most sophisticated weatherproofing systems. Picture a thatcher on a ladder, hand-laying bundles of water, reed or straw like overlapping feathers on a bird's wing, each layer meticulously angled to guide rain downward. The magic wasn't just in the materials but in the craftsmanship. A well-made thatch roof could last half a century, outliving many modern asphalt shingles, all while being fully biodegradable. From the cottages of rural England to the meeting houses of Tahiti, this universal solution emerged independently across continents, proving its timeless effectiveness. What made thatch so resilient? The secret lay in its layered design. Builders didn't just pile vegetation haphazardly, they created a sloping thatch skin often 2 feet thick. The outer layer hardened into a crust from sun and rain, while the inner layer remained spongy, trapping air for insulation. In tropical climates, palm fronds were woven so tightly they could deflect monsoons, while in colder regions like Scandinavia, straw was packed dense enough to block snowmelt. And here's the kicker: thatch breathed. Unlike sealed modern roofs, it allowed moisture to escape, preventing rot and regulating humidity naturally, a feature architects now try to replicate with high-tech vapor barriers. The real marvel was how builders secured it all without a single nail. In Japan, thatchers used bamboo pegs and rice straw ropes, tying roofs down with knots that tightened over time. The Maori of New Zealand layered flax leaves in grids, anchoring them with weighted stones. European thatchers perfected the spar and sway technique, bending hazel branches into hooks that pinned bundles in place. Every culture developed its own artistry, often weaving symbolic patterns into the ridges, a hidden language of protection and prosperity. But perhaps the most surprising thing about thatch is its thermal intelligence. In summer, the hollow stems of reeds acted like tiny air ducts, drawing heat upward and away. Come winter, the same trapped air became an insulating blanket. Some medieval European homes stayed so warm that snow would melt only along the roof's edge, a phenomenon locals called the thatcher's breath. Modern tests show a well-maintained thatch roof can match the insulation value of 6 inches of fiberglass, all without a watt of electricity. Today, a handful of master thatchers still practice these ancient techniques, not as novelties but as sustainable alternatives. In Ireland, some pubs still favor thatch for its unbeatable acoustics and charm, while in Bali, new eco-resorts use coconut palm thatch to blend luxury with low-impact design. It's a reminder that sometimes the best technology isn't the newest, it's the one that's been tested by time. When you see a thatched roof, you're not just looking at shelter, you're seeing a dialogue between human hands and the rhythms of wind, rain, and sun, a partnership as old as building itself. Adobe bricks might look like humble blocks of dried mud, but their simplicity hides a stroke of genius, turning the desert's harshness into an architectural advantage. In places where scorching days gave way to freezing nights, ancient builders discovered that a mix of clay-rich soil, straw, and water could become something extraordinary. Kneaded by foot and molded by hand, this blend was pressed into wooden frames, then left to bake under the sun until it hardened into bricks as durable as stone. The straw wasn't just filler, it acted like a skeleton, preventing cracks as the mud shrank, while the clay particles bonded tightly under the sun's relentless heat. The result, walls that could stand for centuries, like those in New Mexico's Taos Pueblo, where some adobe structures have sheltered families for over 1,000 years. What made adobe so revolutionary was its thermal mass. Unlike modern thin-walled homes that heat up and cool down rapidly, these thick mud walls absorbed warmth during the day like a sponge, then slowly released it at night. In Yemen's ancient skyscrapers, some adobe walls measured 3 feet thick, creating natural air conditioning long before the invention of mechanical systems. The same principle worked in reverse during summer, when the wall's cool interior drew heat from living spaces. Builders even designed tiny ventilation shafts to enhance airflow, proving they understood thermodynamics long before the term existed. But here's the catch: adobe demanded patience. Unlike kiln-fired bricks that hardened in days, sun-dried adobe needed weeks of careful tending. Builders in Mesopotamia would rotate bricks periodically to ensure even drying, while Berber artisans in North Africa added camel dung to the mix, a natural waterproofer that also repelled insects. In the Andes, builders incorporated llama wool for extra tensile strength, creating earthquake-resistant walls that swayed rather than shattered. Every culture adapted the recipe to their environment, turning local soil into a kind of architectural fingerprint. The real beauty of adobe lies in its democracy. Unlike grand stone monuments that required slave labor or vast resources, adobe homes could be built by anyone with strong arms and time. Villages often turned brick-making into communal events where children stomped the mud, women wove straw binders, and men stacked the finished bricks into walls sealed with more mud plaster. This wasn't just construction, it was a ritual that bound communities together. Today, architects are rediscovering adobe's potential as a sustainable alternative. Modern stabilizers like lime or asphalt emulsion address its one weakness, water erosion, while preserving its carbon-neutral benefits. In New Mexico, entire subdivisions now feature adobe homes with solar panels, blending ancient thermal mass with renewable energy. It's a powerful reminder that the best solutions aren't always about inventing something new, but remembering what already worked. When you touch an adobe wall, you're not just feeling mud, you're touching centuries of accumulated wisdom, a quiet rebellion against the idea that progress must mean leaving the past behind. Timber framing was more than just stacking logs. It was a three-dimensional puzzle where every notch, every angle, every hand-carved joint had to bear the weight of generations. Picture a Viking longhouse, its massive oak beams locked together so tightly that storms couldn't shake them, or a Japanese temple standing defiant against earthquakes for 1,200 years. These weren't just buildings, they were feats of engineering without equations, where intuition and craftsmanship replaced computer models. The secret lay in the joints. A mortise and tenon connection, a protruding tongue on one beam slotting into a carved recess on another, could distribute weight so efficiently that some structures survived wars and weathered that toppled stone walls. But here's what's staggering. Builders achieved this precision with nothing more than axes, adzes, and chisels. In medieval Europe, carpenters used a tool called a scribe rule, tracing the unique contours of one timber onto another like a tailor fitting a bespoke suit. A cut too deep, the joint would wobble. Too shallow, the beams might split under pressure. In Japan, temple builders took it further, designing joints that tightened over time as wood naturally shrank, creating structures that grew stronger with age. The famed Horyuji temple near Nara stands today not despite its wooden frame, but because of it, each beam flexing slightly during tremors, then settling back into place like a tree bending in the wind. The real magic of timber framing was its adaptability. In the snowy Alps, builders angled roofs steeply to shed heavy snow, while in monsoon-prone Southeast Asia, they raised floors on stilts to avoid flooding. Viking longhouses used curved trunks for rafters, exploiting the natural strength of wood grain, while Chinese palaces incorporated intricate dugong brackets that acted like shock absorbers. Every culture developed its own vocabulary of joints, dovetails, scarf joints, lap joints, each solving a unique structural puzzle. Yet perhaps the most overlooked aspect was the social ritual behind the craft. Timber framing was often a communal event where raising a barn or hall became a village festival. In Germany, the Richtfest celebrated the moment the final beam was placed, with craftsmen signing their work like artists. These weren't anonymous constructions. They carried the fingerprints of their makers. Quite literally, many joints were tailored to the carpenter's hand, ensuring no two frames were exactly alike. Today, timber framing is experiencing a renaissance, not as nostalgia but as cutting-edge sustainable design. Modern engineers have discovered that wooden skyscrapers can rival steel in strength while storing carbon instead of emitting it. The irony is poetic. The oldest construction method might hold the key to our future. When you see a timber-framed building, you're not just looking at wood. You're seeing a conversation between human hands and the living forest, a reminder that the best technology sometimes grows on trees. Cobb construction turned humble dirt into architecture so enduring that some of these homes still shelter families after 500 years. Unlike rigid bricks or timber, Cobb was alive in the hands of its builders, a pliable mix of clay, sand, straw, and water kneaded into a material as versatile as pottery clay. Picture teams of workers barefoot in pits, rhythmically stomping the mixture until it reached the perfect consistency, then passing globs up to walls being sculpted like giant clay sculptures. Without molds or frames, every curve and niche reflected the builder's touch, resulting in homes that seemed to grow from the earth itself. In Devon, England, entire villages rose this way, their undulating walls and rounded corners softening the landscape rather than conquering it. The magic of Cobb lay in its contradictions. Though molded like soft dough once dried, it hardened into a substance as fireproof as brick and as insulating as modern foam. The straw fibers acted like microscopic reinforcement, preventing cracks while allowing the walls to breathe, regulating humidity naturally. In Morocco's Atlas Mountains, Cobb homes stayed cool in blistering heat thanks to thermal mass principles similar to Adobe, while in Wales, their thick walls trapped warmth so effectively that hearth fires were often unnecessary. And here's the twist: Cobb's greatest weakness, water erosion, became its strength. Unlike stone or wood, damaged sections could be repaired by simply slapping on fresh wet cob, a self-healing property modern materials can't replicate. Building with Cobb was a lesson in patience and community. Teams worked in lifts, adding layers no taller than 2 feet per day to prevent collapse. As each layer dried, a process taking weeks, it became the foundation for the next, creating a monolithic structure without weak seams. In West Africa, entire extended families participated, with children gathering straw, elders supervising mix ratios, and women sculpting decorative niches for storage. The rhythm was as important as the materials. Too much haste and the walls slumped, too little and the lower layers dried unevenly. This wasn't construction, it was a dance with gravity and time. What's remarkable is how Cobb adapted across cultures. In Yemen, builders mixed crushed volcanic stone for extra stability in earthquake zones. The Navajo perfected a version using pinon pine resin as a natural waterproofer, while in Brittany, oyster shells were added for texture and drainage. Every region's cob bore the fingerprints of its environment. Quite literally analyzing historic cob walls can reveal traces of local pollen, livestock hair, even remnants of meals mixed in by accident. Today, cob is experiencing a revival among eco-builders, not for nostalgia but for its unbeatable sustainability. Modern cob homes often incorporate recycled materials, broken glass bottles for light wells, discarded tires as foundations, while maintaining the ancient breathability that prevents mold and dampness. Workshops from Oregon to New Zealand teach the technique to new generations, proving that a method older than the pyramids still has a place in our future. When you walk into a cob home, you're not just entering a building, you're stepping into a legacy of hands shaping shelter from the very earth beneath their feet, a reminder that the simplest materials, when paired with human creativity, can outlast empires. In the blinding white expanse of the Arctic, where temperatures plunge far below freezing and the wind howls like a living thing, the Inuit didn't just survive, they thrived thanks to one of architecture's most elegant innovations, the igloo. At first glance, it seems impossible, a home made of snow that's warmer inside than a wooden cabin. But every detail of this spiraling dome was honed by generations of Arctic wisdom. The secret started with the snow itself. Builders didn't use just any powder. They sought out wind-packed drifts, dense as styrofoam, which could be carved into blocks with bone knives or antler saws. These weren't mere bricks of ice, they were insulating marvels, trapping tiny air pockets that acted like natural fiberglass, slowing the escape of warmth. The real genius lay in the construction. Each block was cut on a slight inward angle, creating a rising curve that locked into place as the dome grew taller. No scaffolding, no supports, just snow leaning on snow, with the final keystone block at the top completing the puzzle. The physics were flawless. The arch distributed weight evenly, making the structure stronger as pressure increased. A well-built igloo could support the weight of a grown adult standing on its roof, yet it required nothing more than a skilled hand and patience. And here's the twist, the interior wasn't frigid. Body heat and the gentle glow of seal oil lamps would melt the innermost layer of snow slightly, which then refroze into a smooth ice glaze. This wasn't a flaw, it was a feature. That thin barrier sealed cracks and reflected heat back inward, creating a microclimate where temperatures could hover near freezing while outside. The Arctic night plunged to -40. But igloos were more than just engineering. They were adaptability incarnate. Temporary hunting shelters might take just an hour to build, while larger family dwellings could include multiple chambers connected by tunnels, with raised sleeping platforms to trap warm air. Some even had windows, thin sheets of freshwater ice that let in muted light while blocking wind. The Inuit didn't fight their environment. They collaborated with it, using snow's properties to their advantage in ways modern materials scientists still study. What's often overlooked is the social ingenuity behind these structures. Building an igloo was rarely a solo task. Families worked together, with children packing snow into crevices while elders directed the spiral's curve. The layout itself fostered community, sleeping areas arranged in a circle to share body heat, entrance tunnels dug below the main floor to trap cold air like a natural airlock. Even the orientation mattered. Doors often faced away from prevailing winds, and some igloos included storage niches carved into walls, turning snow itself into furniture. Today, Arctic researchers and survival experts still train in igloo construction, not as a relic but as a masterclass in efficient design. NASA has even studied their principles for potential lunar habitats. The lesson transcends the Arctic. When resources are scarce, innovation flourishes. The igloo stands as a testament to human creativity, proof that even in the harshest conditions, we don't just endure. We build, we adapt, and sometimes we turn the very thing that should defeat us into our shelter. Carving a home directly into living rock might sound like something from a fantasy novel, but for thousands of years, it was everyday reality for communities from Turkey's Cappadocia to China's lowest plateau. Picture teams of builders working by oil lamp light, chiseling room after room into sheer cliff faces, not as crude holes, but as refined living spaces with arched ceilings, carved shelves, and even staircases spiraling through the stone. These weren't temporary shelters, they were generational projects where each strike of the hammer added another inch to a legacy that would outlast empires. The brilliance of cave dwellings lay in their synergy with the environment. Unlike constructed homes that fight against nature, these spaces worked with it. In Cappadocia's volcanic tuff, a rock soft enough to carve yet strong enough to support multi-story complexes, builders engineered entire underground cities like Derinkuyu, descending 18 levels deep. Hidden ventilation shafts disguised as well-supplied fresh air, while massive circular stone doors could roll shut to seal out invaders. Over in China's Shaanxi province, families carved courtyard homes into lowest cliffs, creating facades with lattice windows that filtered sunlight deep into the rock. The earth itself became both insulation and fortress, maintaining steady temperatures around 60 degrees Fahrenheit year-round. No furnace or air conditioning required. What's astonishing is the precision achieved with rudimentary tools. Without dynamite or jackhammers, progress was measured in inches per day. Builders used iron chisels and wooden mallets, often working from the ceiling downward to prevent collapses. They mapped rooms around natural rock formations, turning weaknesses into features. A protruding boulder might become a hearth, while a fault line could guide the path of a ventilation shaft. In Petra, Jordan, the Nabateans carved elaborate tombs with acoustics so precise that whispers at the entrance could be heard clearly 50 feet inside. This wasn't just excavation, it was stone whispering, but perhaps the most overlooked aspect was the social ingenuity these spaces fostered. In Spain's Sacramento caves, gypsy communities built interconnected homes where sound carried through the porous rock, creating a natural communication network. The Buddhist monks of India's Ajanta caves painted entire scriptures onto their walls, turning functional spaces into illuminated manuscripts of stone. Even the humblest cave homes often featured multiple chambers, sleeping areas dug deeper for warmth, kitchens near entrances to vent smoke, and niches for oil lamps positioned to refract light across curved ceilings. Today, modern architects are revisiting these principles with laser scans and 3D modeling, uncovering how cave dwellers mastered passive ventilation and seismic stability millennia ago. In Tunisia, hotels now offer cave suites that stay cool without AC, while in Australia, opal miners' dugout homes have inspired subterranean eco-resorts. The lesson echoes across time. Sometimes the most advanced shelter doesn't rise above the landscape, it becomes one with it. When you walk through these carved halls, you're not just seeing empty rooms, you're witnessing a conversation between human resilience and the patience of stone, where every chip in the rock tells a story of endurance. Bamboo bends but doesn't break, a quality that transformed it into one of history's most versatile building materials. Across the monsoon-soaked hills of Southeast Asia to the cloud forests of the Andes, cultures separated by oceans discovered the same truth. This fast-growing grass could outperform timber, stone, and even steel in certain applications. Unlike rigid materials that fracture under stress, bamboo's fibrous structure allows it to sway with typhoon winds and rebound after earthquakes, a lesson modern engineers are only now fully appreciating. The secret lies in its anatomy. Those hollow segments divided by nodal walls aren't just lightweight. They're nature's version of reinforced concrete, with silica-rich fibers running longitudinally like built-in rebar. Consider the scaffolding of Hong Kong's skyscrapers, where bamboo poles lashed together with nylon straps, a technique adapted from ancient vine bindings, still rise dozens of stories high. Workers scramble up these springy frameworks with the agility of squirrels, trusting a material that's been tested for millennia. In Colombia, the guadua bamboo species grows so robust that bridges built from it can support trucks weighing several tons, yet decompose harmlessly when retired. But perhaps the most ingenious adaptation was in Japan, where Shinto shrines used bamboo gutters not just for drainage, but as natural earthquake dampers. The stem's slight flex dissipated seismic energy, protecting delicate wooden structures above, an ancient precursor to today's base isolation systems. What's often overlooked is the sophistication of traditional joinery. Builders didn't just nail bamboo together, they mastered friction fit techniques where moisture would tighten connections over time. In the Philippines, split bamboo strips were woven into panels called sawali, creating walls that breathed like living skin, while in Bali, whole culms were charred slightly to repel insects, a chemical-free preservation method still used today. The Maya took it further, embedding hot stones into bamboo poles to curve them for vaulted roofs, a technique visible in the ruins of Tikal. Sustainability wasn't an afterthought, it was baked into the process. While an oak tree might take 80 years to mature, bamboo reaches structural strength in just 3 to 5 years, and harvesting it stimulates new growth. Villages managed bamboo groves as living warehouses, rotating harvests to ensure perpetual supply. Compare that to modern construction, where a single steel beam's production emits as much carbon as a car driven 12,000 miles, and you start to see why architects from Bali to Berlin are revisiting this ancient material. Today, engineered bamboo laminates are pushing boundaries even further. Treated strands pressed into planks rival the strength of industrial alloys, leading to ventures like Bali's Green School, where entire campuses spiral skyward from bamboo arcs. Yet the real magic persists in the old ways, the rhythmic tapping of mallets as craftsmen split culms along their grain, the intricate lashing patterns passed down through generations. When you see a bamboo structure, you're not just looking at a building material. You're witnessing a dialogue between human ingenuity and a plant that teaches us resilience isn't about resisting forces, but learning how to move with them. On the vast, treeless prairies where the wind carved waves in the grass, settlers faced a challenge: how to build shelter when the nearest forest was hundreds of miles away. Their solution lay beneath their feet: sod, not just dirt, but thick mats of soil knitted together by the dense roots of prairie grasses like buffalo grass and blue grama. These weren't mere clumps of earth. They were nature's prefabricated building blocks, cut from the ground in foot-thick slices with a special plow called a grasshopper. Imagine stacking these living bricks like a giant's loaf of bread, each layer's tangled roots acting as a biological mortar that bound the walls together. The result, homes that rose from the very land they stood on, their earthy walls blending into the horizon as if the prairie itself had decided to cradle its newcomers. What made sod houses so remarkable was their dual nature, both temporary and enduring. Early settlers often built them as stopgap shelters while dreaming of wooden frame houses, only to discover these humble structures outlasted their expectations. The thick earth walls, sometimes 2 to 3 feet wide, created incredible insulation. In the blistering summers, interiors stayed mercifully cool, while winter's fiercest winds couldn't steal warmth from the snug rooms. Families in Nebraska and the Dakotas reported waking up to frost on their blankets, not from cold, but from their own breath condensing against the sod ceiling, proof of how effectively these walls trapped heat. And when blizzards buried entire towns, sod houses became underground havens, their occupants warm beneath a quilt of snow that only added another layer of insulation. But living with earth came with earthy challenges. Heavy rains could turn roofs into sieves, dripping mud onto beds and tables until the sod's roots re-knit. Insects, from ants to the occasional snake, treated walls like extended habitats. One settler's diary recounts waking to find a cow grazing on their roof, a surreal hazard of building with what livestock considered breakfast. Yet settlers adapted with pragmatism. They whitewashed interior walls with lime to brighten dim spaces and repel bugs, hung muslin ceilings to catch falling debris, and learned to angle roofs steeply to shed water. Some even planted fresh grass on their homes' exteriors, turning problems into aesthetics, a living facade that swayed with the seasons. The real ingenuity lay in the details. Without timber for door frames, builders rolled up sod into columns, packing them tight as stone. Windows were precious commodities, often just 1 or 2 panes salvaged from wagons or ordered months in advance. Chimneys might be cobbled together from tin cans or clay, while floors ranged from packed earth to planks if a homesteader struck lucky. Furniture, too, was born from necessity, sod benches softened with hay, shelves carved into walls, and beds suspended from ceiling ropes to avoid dampness. These weren't just houses, they were experiments in making do, where every solution whispered the prairie's lesson. Scarcity breeds invention. Today, a handful of preserved soddies stand as testaments to this chapter of ingenuity. At Nebraska's Homestead National Monument, visitors can step inside a reconstructed home and feel its hushed stillness, the way the walls mute even prairie winds. Modern engineers marvel at their passive climate control, with some eco-builders reviving earth-sheltered designs inspired by these pioneers. There's poetry in that, the same material that once symbolized hardship now guiding sustainable architecture. When you touch a sod wall, you're not just feeling dirt, you're touching the resolve of people who looked at an endless sea of grass and saw not just obstacles, but possibilities. In an age of disposable housing, that's a legacy worth remembering. On the shimmering wetlands where land and water dance an endless waltz, ancient builders turned the very reeds beneath their feet into floating worlds. In the marshlands of southern Iraq, where the Tigris and Euphrates rivers braid together, the marsh Arabs constructed entire villages that rose and fell with the seasons, not on solid ground, but on great rafts of bundled reeds called tuhul. These weren't crude platforms but engineered marvels, where layers of kasab reeds, some as thick as a man's arm, were lashed together with date palm fibers into buoyant foundations. The secret wasn't just in the material but in the craftsmanship. Builders would harvest reeds at their peak strength, then dry and bundle them so tightly that air pockets formed natural flotation chambers. A single well-made raft could support the weight of a family's home for years, all while bobbing gently on the water like a leaf. What's astonishing is how these floating homes defied conventional construction. Without a single nail or drop of tar, builders relied entirely on tension and geometry. The reed's natural silica content made them resistant to rot, while their hollow stems trapped air like microscopic life jackets. In Peru's Lake Titicaca, the Yoros people took this further, weaving totora reeds into islands so stable they could anchor hearth fires without burning. Each home was a lesson in flexibility. When lower layers became waterlogged, new bundles were simply added atop the old, creating a living foundation that renewed itself over time. During floods, these floating villages would rise effortlessly with the waters, while neighboring towns on solid land drowned. the real genius lay in the details. Marsh Arab houses often featured arched reed roofs that shed rain like palm fronds, while Euro's builders twisted reeds into ropes strong enough to moor their islands to the lakebed. Furniture, too, sprang from the reed sleeping mats woven tight enough to repel scorpions, storage baskets that doubled as flotation devices, even children's toys shaped from leftover cuttings. Every part of the plant served a purpose, embodying a zero-waste philosophy long before the term existed. But perhaps the most remarkable thing was how these communities thrived in flux. When a reed platform grew too heavy, families would paddle their entire home to shallower waters, slicing off the sodden base to lighten the load. In Titicaca, islanders would rotate their structures periodically to ensure even wear, a practice called turning the earth without any earth at all. These weren't just houses, they were living systems as responsive to their environment as the herons nesting in the reeds nearby. Today, a handful of these traditions survive, not as museum exhibits but as vital adaptations. Modern engineers study reed construction for clues to sustainable floating cities, while artists replicate the techniques for installations that drift between art and architecture. When you see a photograph of a reed island, you're not just looking at shelter, you're seeing a dialogue between human hands and the rhythms of water, a reminder that sometimes the most enduring homes aren't anchored to the ground, but to the wisdom of working with, not against, the elements. Animal hide tents didn't just provide shelter, they embodied an entire way of life, transforming raw materials from the hunt into mobile homes as sophisticated as any modern camper. Picture a Plains indigenous family on the move, their travois loaded with carefully rolled bison hides and slender lodgepole pines. Within hours, these elements would rise into a spacious conical tipi, its smoke flaps adjusted to catch the breeze, its painted designs telling stories under the vast sky. This wasn't just a tent, it was a masterpiece of nomadic engineering, honed over generations to balance portability with resilience. The secret started with the hides themselves. Unlike today's synthetic fabrics, bison or reindeer skins were tanned with brains, smoke, or fish oil, a chemical-free process that made them supple yet water-repellent. Stitched together with sinew thread that tightened when wet, the coverings became nearly impervious to storms, while still allowing enough airflow to prevent condensation, a problem modern tents still struggle with. The real genius lay in the geometry. The tipi's conical shape was no accident, its sloping sides deflected wind like an aerodynamic shell, while the slight inward tilt of poles created a self-supporting tension. In Mongolia, the jur or yurt took this further, with its lattice walls compressing for transport yet expanding to create circular spaces large enough for entire families. Both designs shared a clever trick: adjustable ventilation. Tipis featured smoke flaps that could be angled to create a draft, drawing smoke upward while keeping rain out. Jur roofs had a central wheel that could be cracked open in summer or sealed tight in winter blizzards. These weren't static structures, they breathed with the needs of their inhabitants. What's often overlooked is the social intelligence behind these designs. The circular floor plans fostered community. No corners meant no hierarchy, with seating arranged so everyone faced one another equally. The hides themselves were more than roofing, they were climate control. Dark bison skins absorbed sunlight in winter, while lighter caribou hides reflected summer heat. Some Siberian tribes even layered reindeer fur with the hairs facing outward in winter to shed snow, then reversed them in summer for better airflow. Every stitch held purpose. The Cheyenne reinforced stress points with extra hide patches, while the Sami sewed intricate smoke channels into their lavu, tents to protect precious reindeer herds sheltering alongside them. Building these tents was a communal art, Among the Lakota, women owned and erected the tipis, their expertise in aligning the poles ensuring stability. The Kazakhs felt a properly tensioned jerk cover should sound like a drum when tapped, a quality check passed down through oral tradition. Even the tools reflected ingenuity: bone needles for piercing thick hides, wooden mallets for driving stakes into frozen ground, and painted symbols that served as both decoration and spiritual protection. Today, NASA studies these designs for potential Mars habitats, while modern glampers pay thousands for replicas with titanium frames. Yet the originals cost nothing but skill and respect for the animals that provided them. When you see a hide tent, you're not just looking at a shelter, you're witnessing a dialogue between movement and home, where every knot and seam whispers the wisdom of those who knew how to carry their world with them. Stone circles stand silent under the open sky, their massive stones arranged with a precision that defies their ancient origins. These weren't just random piles of rock. They were celestial calendars, community gathering places, and perhaps even bridges between worlds. Take the Ring of Brodgar in Scotland's Orkney Islands, where 60 megaliths once formed a perfect circle, nearly 140 feet across. Moving just one of these 20-ton stones would challenge modern equipment, yet Neolithic builders transported them miles across rugged terrain using nothing but ropes, wooden sledges, and teams of workers singing in rhythm to coordinate their pulls. The grooves still visible on some stones reveal their journey drag marks from being hauled over log rollers that acted like primitive conveyor belts, a technique also used to build Egypt's pyramids. What's truly breathtaking is how these builders married brute strength with celestial mathematics. At Callanish Stones in Scotland's Outer Hebrides, the central monolith aligns perfectly with the moon's 18.6-year cycle, marking when our satellite appears to graze the horizon in a phenomenon called the lunar standstill. Over in England's Avebury, the largest stone circle in Europe forms a snake-like pattern that mirrors the Milky Way's curve during summer solstice. These weren't crude observations. They required generations of meticulous sky watching, with knowledge passed down through oral traditions long before written records existed. The stones themselves became frozen shadows, permanent markers of celestial events that dictated planting, harvesting, and sacred ceremonies. The spiritual dimension runs deep in these circles. In Ireland's Grange Circle, the entire structure acts like an acoustic chamber stand at its center, and your voice resonates unnaturally, as if the stones themselves were amplifying sound. At Germany's Goseck Circle, the oldest known solar observatory in Europe, winter solstice sunlight pierces through precisely aligned gates to illuminate an altar. Some researchers believe these sites functioned as prehistoric universities, where initiates learned astronomy, geometry, and the interconnectedness of life. The circular shape itself held meaning, no beginning or end, echoing cycles of seasons, life, and death. Perhaps most humbling is realizing these projects spanned generations. The 30 sarsen stones at Stonehenge, each weighing up to 50 tons, were dragged nearly 20 miles from Marlborough Downs around 2500 BC, a journey that might have taken 500 people 2 years just for transport. Then came the shaping, using stone mauls to chip each megalith into precise trapezoids, their sides subtly tapered to create perspective illusions when viewed from below. The lintels weren't merely dropped atop, they were secured with mortise and tenon joints and tongue and groove connections worthy of fine carpentry. All this without metal tools, wheels, or written plans, just collective memory and shared purpose. Today, archaeologists using laser scans discover new layers of sophistication. Some Welsh bluestones at Stonehenge bear musical properties when struck. They produce metallic tones that might have been used in rituals. Other circles like Portugal's Almenda's cromlech show carved spiral patterns that mirror petroglyphs found worldwide, suggesting a shared symbolic language. Modern druids and astronomers still gather at these sites, proving their power endures. When you walk among these silent sentinels, you're not just seeing rocks, you're witnessing humanity's first cathedrals, built not to divide earth and sky, but to unite them. Earth-burming turned the very ground beneath our feet into a living blanket for homes, wrapping structures in a hug of soil that kept them warm in winter and cool in summer. Picture a Viking longhouse nestled into a hillside, its sod roof blending seamlessly with the landscape, only the carved wooden doorway and a wisp of smoke revealing human presence. This wasn't just camouflage, it was climate control perfected over centuries. By burying a home's north and side walls into the earth, builders tapped into the planet's natural thermal mass. The soil, slow to heat and slow to cool, acted like a giant temperature buffer. In Norway's freezing winters, burmed homes stayed a staggering 40 degrees warmer than exposed buildings, while in the scorching summers of the American Southwest, Pueblo dwellings built into cliffs remained refreshingly cool without a single watt of electricity. The brilliance of burming lay in its simplicity and adaptability. On the windswept plains where the Lakota built their earthen lodges, the berm blocked punishing gusts that could steal heat from even the sturdiest walls. In Iceland, where volcanic soil insulated better than modern fiberglass, settlers layered turf over stone foundations, creating homes so efficient that hearth fires were often unnecessary. But perhaps the most ingenious detail was the orientation. Nearly every burmed home, from Viking dwellings to Mandan earth lodges, faced south, an ancient understanding of passive solar design. Low winter sun would stream through doorways, warming packed earth floors that radiated heat all night, while summer's high sun was blocked by roof overhangs. Some Native American structures even incorporated reflective pools of water or light-colored stones to bounce additional sunlight inside. What's often overlooked is how burming fostered community. These weren't solitary structures, but often clustered villages where shared earth walls created natural sound barriers and windbreaks. At Colorado's Mesa Verde, entire cities were carved into cliffs, their terraced designs allowing warm air to rise through the community while cold air drained into lower chambers. In Denmark, early medieval pit houses were dug several feet below ground, their sunken floors creating microclimates where families could gather around central fires without losing precious warmth to drafts. Modern architects are now revisiting these principles with startling results. In Switzerland's Vals Valley, the Therme Vals Spa Hotel uses earth-burming to maintain perfect temperatures year-round, while in Montana, contemporary, earth-sheltered homes reduce energy costs by up to 80%. The irony is profound. A technique born from necessity now guides cutting-edge sustainable design. When you see a burmed home, you're not just looking at a building, you're witnessing a conversation between human ingenuity and the patient wisdom of the earth itself, where the oldest solution might just be the most advanced. On sun-drenched atolls where trees were scarce and importing stone unthinkable, islanders turned to an unlikely architect, the ocean itself. Coral reefs, built over centuries by tiny polyps, became the foundation for entire cities. Workers would wade into shallow lagoons at low tide, carefully harvesting blocks of living coral with wooden wedges and stone tools. Unlike quarrying stone, this was a delicate dance with nature, taking just enough to build while leaving the reef to regenerate. The harvested coral was then left to dry in the sun, a process that transformed the porous skeletons into surprisingly sturdy building blocks, light enough to carry yet strong enough to withstand cyclones. What made coral construction so ingenious was how it embraced the material's quirks. Those tiny holes and channels that made coral look fragile were actually its secret weapon. The porous structure allowed walls to breathe, preventing moisture buildup in humid climates while dissipating the force of hurricane winds like a sponge absorbing a punch. Builders in the Maldives and Seychelles stacked these blocks in alternating patterns, much like bricklaying but with a twist. They used coral lime as mortar. Made by burning smaller coral pieces in kilns, this natural cement was perfectly adapted to its environment. Unlike imported mortar that would crumble in salt air, coral lime actually hardened over time as it reabsorbed minerals from the sea breeze, becoming stronger with each passing monsoon. The real mastery lay in the details. In Zanzibar's stone town, craftsmen carved intricate Arabic inscriptions directly into coral facades, their chisels revealing the material's unique grain, softer than limestone yet more resistant to erosion. On Fiji's Lau Islands, builders mixed crushed coral with coconut oil to create a waterproof plaster, while in the Gilbert Islands, entire seawalls were constructed from massive coral boulders fitted together like a three-dimensional puzzle. Even the shapes of the blocks told a story. Some were cut into fan-like wedges to create curved walls, while others were left irregular to maximize structural interlocking. But perhaps the most remarkable thing was the sustainability baked into this method. Coral buildings required no deforestation, no mining, and no long-distance transport. When a structure was dismantled, the blocks could be returned to the ocean to replenish the reef or crushed back into lime for new construction. Modern engineers are now studying these principles, experimenting with lab-grown coral for coastal restoration projects. Walking through the coral alleys of Lamu Old Town or the Maldives Athimu Ganjavaru, you're not just seeing architecture, you're witnessing a conversation between land and sea, where every block remembers the rhythm of the waves that shaped it. Today, as rising seas threaten modern concrete structures, these ancient coral buildings stand resilient, their lime mortar self-healing with each tide, their porous walls sighing comfortably in the humidity. They whisper a lesson we're only now relearning. The best building materials aren't always the ones we force onto a landscape, but the ones the landscape offers us if we're patient enough to listen. Log cabins stand as monuments to frontier ingenuity, where every notch and gap told a story of survival. Picture a settler family in the dense forests of Pennsylvania or the wilds of Kentucky, felling trees with nothing but broadaxes, then carefully scoring each log with V-shaped notches at the ends. These weren't random cuts, they were precise mathematical joints, designed to interlock like giant Lincoln logs so tightly that even hurricane-force winds couldn't pry them apart. The magic lay in the corners where overlapping logs created a self-supporting grid. No nails, no metal brackets, just friction and gravity holding tons of timber in perfect balance. Some Swedish and Finnish settlers brought an even more refined technique called saddle notch, carving concave seats into logs that hugged the one below like pieces of a wooden jigsaw puzzle. But the real secret weapon was in the chinking the filler between logs that kept out winter's bite. Early builders used whatever the land provided, a sticky mix of clay and animal hair, mashed moss soaked in water, even split wood wedges hammered into gaps. In Appalachia, settlers discovered that a mortar made from crushed limestone and hog bristles hardened like concrete, while Scandinavian immigrants mixed sawdust with pine pitch to create a flexible seal that moved with the logs as they settled. These weren't just insulation methods, they were lessons in listening to the forest. A well-chinked cabin could stay 20 degrees warmer than the outside air, with walls so thick that a Civil War-era diary recounts bullets embedding in logs without penetrating the interior. What's often overlooked is how these humble structures became classrooms of frontier engineering. settlers quickly learned which trees worked best: white pine for its straight grain and easy splitting, cedar for its natural rot resistance, oak for unmatched strength. They'd position the heaviest logs at the bottom, often leaving the bark on for extra weather protection, and orient the cabin's door away from prevailing winds. Roofs sloped sharply to shed snow, while stone footings prevented ground moisture from rotting the first course of logs. Some clever builders even incorporated a cantilevered second story, where upper logs protruded outward to create extra space without needing larger foundations. The social dimension was just as fascinating. Raising a cabin was rarely a solo endeavor. Neighbors would gather for house-raising bees, turning back-breaking labor into a festival of shared effort. Skilled notchers earned reputations like master chefs, their corner work admired like fine joinery. Women often directed the chinking process, passing down recipes for mortar that varied by region like culinary traditions. And when a family outgrew their cabin, they'd simply dismantle it, numbering the logs to reassemble on new land, an early form of modular housing. Today, modern engineers marvel at log cabins' passive survivability. The thermal lag of solid wood means interior temperatures stay stable for days without heating or cooling, a principle now studied for off-grid homes. In Finland, contemporary log hotels boast insulation values rivaling fiberglass, while in Montana, fireproofed log homes withstand wildfires that melt conventional houses. The humble log cabin endures not as a relic but as a testament to a radical idea, that the best shelter might not come from conquering nature, but from understanding it one carefully notched log at a time. Digging down instead of building up might seem counterintuitive, but for indigenous communities across the American Southwest and Siberia's frozen taiga, pit houses represented the perfect marriage of shelter and thermodynamics. Picture a circular pit, 6 to 8 feet deep and 20 feet across, painstakingly excavated with nothing but antler picks and woven baskets. The floor wasn't just flat earth. It often featured a central fire pit surrounded by carefully leveled benches for sleeping, with a strategically placed air vent channeling smoke upward while drawing fresh air through the entrance tunnel. This wasn't mere shelter, it was subterranean climate control perfected over generations. The surrounding Earth, maintaining a steady 55 degrees Fahrenheit year-round, created a natural buffer against desert heat waves and Arctic blizzards alike. In New Mexico's high desert, ancestral Puebloan pit houses stayed a comfortable 60 degrees when surface temperatures swung from scorching to freezing within the same day. The real genius lay in the roofing technique. After digging the pit, builders would erect a conical framework of logs, often juniper or pine, then layer them with brush, grass, and finally a thick blanket of packed earth. The result, a living roof that sprouted wildflowers in spring while insulating like modern fiberglass. In Siberia's Evenki pit houses, reindeer hides stretched over the frame added another insulating layer, with the animal's own body heat helping warm the space during 40 below winters. But perhaps the most ingenious detail was the entryway, a narrow, downward sloping tunnel that acted as a cold air trap. Warm air rising from the central fire would draw chilly drafts down into this passage, where they pooled harmlessly below the main living area instead of flooding the interior. Labor intensity became long-term payoff. Without backhoes or dynamite, digging a single pit house required removing nearly 40 cubic yards of soil, about 3 dump truckloads using only stone tools and human effort. Yet communities deemed this worthwhile because the structures often lasted decades with minimal maintenance. The Pawnee of the Great Plains lined their pit house walls with tightly woven willow mats to prevent cave-ins, while the Mongolian Tsotan reinforced theirs with interlaced horsehair ropes that flexed during earthquakes. Some pit houses evolved into semi-permanent villages with interconnected chambers for storage, ceremonies, and even rudimentary saunas where heated stones generated steam. Modern architects still study these designs for passive heating solutions. The Taos Pueblo's underground kivas inspired contemporary earth-sheltered homes, while Siberian pit house principles inform Arctic research stations. There's profound wisdom in these sunken rooms. They teach us that comfort doesn't always come from dominating our environment, but from nestling intelligently within it. When you stand at the edge of one of these ancient depressions, you're not looking at a hole in the ground. You're seeing a masterclass in making warmth from cold soil and coolness from blazing sun, all without breaking the earth's skin more than absolutely necessary. Along the misty shores where land meets sea, coastal tribes turned what many would consider waste into architectural gold, shell middens. These towering piles of discarded oyster, clam, and mussel shells might have looked like simple refuse heaps, but over generations they transformed into something extraordinary. Crushed and mixed with soil, shells became a versatile building material, creating floors that stayed dry during floods and walls that breathed with the salty air. The magic wasn't just in the shell's abundance, but in their unique properties. Their curved shapes interlaced like nature's puzzle pieces, creating air pockets that improved drainage while their calcium carbonate content acted as a natural binder, slowly cementing layers together underfoot. The brilliance of shell midden construction lay in its layered approach. Tribes from Florida's Calusa to the Pacific Northwest's Chinook would alternate shells with clay and sand, packing each stratum by hand or with wooden tampers. Over time, foot traffic and rain compacted these layers into surfaces as hard as concrete yet far more forgiving. In Florida's coastal villages, floors made this way resisted sinking even in swampy ground, while in British Columbia, shell-rich walls regulated indoor humidity critical in rainy climates where mold threatened stored food. Some middens were intentionally shaped into terraces or platforms, elevating homes above storm surges with what amounted to recycled seafood dinners. What's often overlooked is the sustainability woven into this practice. Unlike modern construction waste that clogs landfills, shell middens were part of a closed-loop system. Harvesting shellfish fed communities, and the waste then sheltered them. The shell's alkalinity even sanitized surrounding soil, reducing parasites, a side benefit ancient builders likely noticed. Archaeologists have found middens repurposed over centuries, with new layers added as older ones hardened. At Georgia's Sapelo Island, shell-based structures from 3,000 years ago remain intact, their surfaces polished smooth by generations of bare feet. The real ingenuity emerged in the details. Some tribes mixed crushed shells with animal fat to create waterproof plasters, while others pressed whole shells into exterior walls as decorative patterns that also diverted rainwater. In Chesapeake Bay, oyster shells were laid concave side down in walkways, creating non-slip surfaces that channeled moisture away. Modern engineers now study these techniques, noting how shell composites resist salt corrosion better than Portland cement, a revelation for coastal infrastructure. Today, a handful of conservationists and indigenous builders are reviving the practice, not as a historical curiosity, but as a viable green building method. In Louisiana, projects like the Point Ochine Shell Midden Restoration demonstrate how these ancient materials can stabilize eroding shorelines. When you walk on a shell midden floor, you're treading on more than history. You're stepping into a philosophy where nothing is truly wasted, and every resource, even a cracked oyster shell, holds potential waiting to be unlocked. Among the rolling green hills of Ireland and Scotland, clusters of beehive huts stand like stone igloos, their curved walls defying gravity without a drop of mortar. These weren't crude shelters but masterclasses in corbelling, an ancient technique where each circle of stones tilts slightly inward, overlapping the layer below like petals closing into a bud. The magic wasn't just in the stacking but in the precision. Builders hand-selected flat stones, testing each one's balance before placing it, sometimes shaving edges with smaller rocks to achieve the perfect fit. As the walls rose, the overhang grew bolder until the final capstone locked the entire structure into a self-supporting dome. The result, a roof so watertight that rain rolled off like a duck's back, and walls that stood firm against Atlantic gales that could topple modern fences. What's astonishing is the physics at play. The corbelled shape distributed weight evenly, channeling forces downward along the curve instead of outward where walls might buckle. In Scotland's Hebrides, some huts feature double walls with crushed stone fill, an early form of cavity wall insulation that trapped warmth while allowing moisture to escape. The interiors, often coated with lime wash, stayed surprisingly bright as light bounced off the pale surfaces. And though they look small from the outside, many huts open into spacious chambers once you duck through the low doorway, a design quirk that kept cold drafts at ankle level while preserving heat where it mattered most. The real ingenuity lay in the adaptations. On Skellig Michael, a windswept island monastery off Ireland's coast, monks built clusters of these huts with interconnecting passages, creating communal spaces where they could study and pray without braving the elements. Some Highland versions incorporated a clever trick, a thin gap between the outer stones and inner lining, creating natural ventilation that prevented condensation, a feature modern architects now call a rain screen. Others, like those in Portugal's Alentejo region, used slate instead of sandstone, proving the technique transcended local materials. But perhaps the most humbling aspect is the endurance. Many beehive huts still stand after 1,200 years, their stones untouched by repairs. Modern engineers have tested replicas, subjecting them to hurricane-force winds and torrential rain, only to find the structures outperform contemporary designs in wind resistance and drainage. There's poetry in that, a building method older than the English language outlasting steel and concrete. When you run your hand along the curve of a beehive hut, you're not just touching rocks, you're feeling the quiet confidence of builders who knew how to make gravity their ally, one carefully chosen stone at a time. In the sun-scorched landscapes of Australia, where temperatures swing from blistering heat to chilling desert nights, Aboriginal peoples turn to an unlikely architect, the humble paperbark tree. With bark that peels away in thick, felt-like sheets, these trees offered more than just shade. They provided the raw materials for shelters that were both ingenious and ephemeral. The process began with careful selection. Not every tree would do. Elders taught which trunks had bark at the perfect stage of growth, thick enough to provide insulation yet supple enough to bend without cracking. Using stone tools or sharpened shells, builders would make precise vertical incisions, then peel the bark away in large swaths, sometimes as wide as a person is tall. This wasn't destruction but careful stewardship, as the trees would regenerate their bark over time, allowing the same resource to be harvested again years later. What made paperbark so revolutionary was its natural engineering. The bark's layered structure, dense and waterproof on the outside, soft and fibrous beneath, created a built-in insulation system. When draped over a framework of saplings or tied into dome shapes, the outer surface shed rain like modern roofing felt, while the inner layer trapped pockets of air, moderating temperatures inside. In the tropical north, where monsoon rains could last for weeks, shelters were often built with steeply angled bark roofs to channel water away, while in arid central regions, low-slung designs maximized shade and minimized heat absorption. Some groups even layered bark sheets like shingles, overlapping them to create seamless coverage that could withstand cyclonic winds. The construction process itself was a lesson in efficiency. A family could assemble a sturdy shelter in hours, using nothing more than bark, twine made from plant fibers, and the occasional daub of mud to seal gaps. The portability was game-changing. Entire communities could roll up their bark walls and carry them to new hunting grounds, leaving no trace on the land. This wasn't just shelter, it was a philosophy of lightness, a way of living that prioritized mobility and minimal environmental impact long before those terms entered modern sustainability discussions. But perhaps the most overlooked brilliance lay in the cultural knowledge encoded in these structures. Different groups developed distinct styles. The Yolngu of Arnhem Land created elegant arched roofs by threading bark through with vines, while the Noongar in the southwest wove multiple layers into quilted walls for extra insulation. Some shelters incorporated smoked bark to repel insects. Others were lined with kangaroo skins for added warmth. The very act of building was intergenerational, with children learning by gathering materials, elders demonstrating knot-tying techniques, and everyone sharing in the rhythmic work of shaping pliable bark into three-dimensional forms. Today, architects are rediscovering paperbark's potential. Researchers have found that its natural thermal properties rival synthetic insulation, while its biodegradability offers a blueprint for zero-waste design. In some Aboriginal communities, traditional bark shelters still stand beside modern houses, not as relics but as living testaments to a technology that's never gone out of style. When you run your hand along a sheet of paperbark, you're not just touching a building material. You're feeling the quiet genius of people who understood that the best shelters don't fight against nature, but unfold from it, flexible and resilient as the land itself. Walking across a Scandinavian hillside, you might not even notice the homes nestled into the landscape until you spot smoke curling up from a patch of wildflowers where a roof should be. Turf roofing wasn't just camouflage, it was a masterclass in working with nature rather than against it. Picture a Viking builder standing atop a freshly constructed longhouse, carefully unrolling sheets of birch bark like ancient shingles. This wasn't mere decoration. That bark, rich in natural oils, formed an impermeable barrier against rain and snow. But the real magic happened when they layered sod atop it, transplanting entire sections of meadow complete with grasses, herbs, and even small shrubs. The result, a living roof that breathed with the seasons, its roots weaving through the soil to create a mat so dense it could withstand Arctic gales. What made these roofs so ingenious was their layered intelligence. Starting from the top down, the grass and wildflowers acted as a thatch-like shield, their leaves dispersing rainfall before it could penetrate. Beneath them, the dense turf, often cut from nutrient-rich marshlands, formed a spongy insulation layer that trapped heat in winter and blocked solar radiation in summer. Historical records from Norway's stave churches show interior temperatures varied less than 10 degrees year-round, despite exterior swings of 70 degrees or more. The birch bark beneath wasn't just waterproofing. Its silver underside reflected heat downward during cold months, while the cork-like air pockets in its structure provided additional insulation. Maintenance was an art in itself. Farmers would periodically mow their roofs with scythes to prevent overgrowth, sometimes sending goats up to graze, a natural lawn service that also fertilized the soil. In spring, homeowners might replant bare patches with hardy species like thyme or sedum, chosen for their shallow roots and drought resistance. This wasn't just upkeep, it was a form of cultivation, turning roofs into elevated gardens that attracted pollinators and even provided medicinal herbs. Icelandic sagas mention families harvesting angelica and yarrow from their rooftops during harsh winters when ground-level plants were buried under snow. The environmental benefits were staggering. A single square meter of turf roof could absorb up to 50 liters of rainwater during storms, slowly releasing it through evaporation. A natural flood control system that modern cities now spend millions to replicate with concrete infrastructure. The vegetation also captured dust and pollutants, while the soil's microbiome broke down airborne toxins. Archaeologists have found that some Viking-age turf roofs lasted over 70 years with proper care, outliving the wooden structures they protected. Today's green roof movement owes much to these ancient practices. Modern versions use synthetic membranes instead of birch bark and engineered soils rather than hand-cut turf, but the principles remain unchanged. In Oslo, the Opera House's sloping green roof echoes the archipelago's contours, while in Chicago, City Hall's rooftop garden reduces urban heat island effects using the same thermal mass principles Viking builders discovered centuries ago. The irony is profound. A technology born from scarcity, lack of durable roofing materials in treeless Arctic regions, now leads sustainable design worldwide. When you see a turf roof, you're not just looking at a building technique. You're witnessing a philosophy where shelter doesn't conquer nature but invites it to grow alongside human lives, blade of grass by blade of grass. Along Florida's marshy coastlines, where limestone quarries were scarce but oyster reefs stretched for miles, early settlers stumbled upon a brilliant workaround turning seafood waste into building gold. Picture a frontier family roasting piles of oyster shells in a homemade kiln, the flames reducing the tough calcium carbonate shells into a fine white powder, lime. This wasn't just a substitute for traditional mortar, it was a stroke of circular economy genius, transforming discarded shells, once a nuisance underfoot, into the glue that held homes together. The process was deceptively simple. Shells were layered with wood in earthen pits, fired for days until they crumbled into quicklime, then slaked with water to create a putty that could bind sand into concrete as hard as the reefs it came from. What made this shell lime so remarkable was its adaptability. Unlike imported lime that could degrade in Florida's humid salt air, oyster-based mortar actually thrived in coastal conditions. The shell's natural impurities, traces of salt and organic compounds, acted like secret ingredients, creating a binder that resisted erosion from brackish winds and driving rains. At St. Augustine's Castillo de San Marcos, historians found oyster lime mortar in the coquina walls still intact after 3 centuries, while nearby structures built with conventional materials crumbled. The secret, oyster lime's slower curing process allowed it to form microscopic crystals that interlocked like chainmail, making it tougher over time. But the real innovation lay in the logistics. Without roads or heavy machinery, transporting quarried stone was nearly impossible for early Floridians. Oysters, on the other hand, were everywhere harvested daily for food, their shells piling up in middens taller than a person. These waste heaps became accidental quarries, with settlers recycling them into foundations, chimneys, and even entire walls. In Key West's oldest neighborhoods, you can still spot tabby constructions, a mix of shell lime, sand, and whole oyster shells, where the aggregate peeks through like fossilized confetti. Some builders took it further, pressing whole shells into wet mortar as decorative elements, their iridescent interiors catching the light like natural mosaics. The environmental wisdom embedded in this technique is staggering. Modern studies show oyster lime production required just 1/5 the energy of traditional limestone processing, with a carbon footprint dwarfed by today's Portland cement. Even the kilns were sustainable, often temporary earth mounds that left no permanent scar on the landscape. And unlike modern concrete that cracks under saltwater exposure, shell-based tabby actually self-repaired to a degree, as dissolved minerals in coastal air filled microscopic gaps with new crystalline growth. Today, this forgotten technology is making a comeback. Archaeologists working on historic restorations have revived the art of shell lime production, while marine biologists champion oyster reef restoration, partly for ecosystem benefits, partly to revive this ancient building loop. In Apalachicola, a new generation of architects experiments with tabby blends for flood-resistant foundations, proving that sometimes progress means rediscovering what was already working. When you run your hand over an old tabby wall, you're touching more than just a building material. You're feeling a conversation between hunger and shelter, between what's eaten and what endures, a reminder that the best solutions often lie not in conquering an environment, but in thinking like part of it. High on the sun-baked cliffs of the American Southwest, tiny stone rooms cling to the rock face like swallows' nests, proof that sometimes the best place to store a harvest isn't on the ground, but suspended between earth and sky. The ancestral pueblones didn't just stash their corn and beans in these aerial pantries for the view. They engineered them with the precision of military strategists. Each granary, no larger than a modern walk-in closet, was positioned with meticulous care north-facing to avoid scorching summer heat, tucked beneath overhangs to stay dry during monsoon rains, and high enough that even the most determined pack rats would need mountaineering skills to raid them. What made these cliffside vaults so ingenious was their multi-layered defense system. The approach alone was a deterrent. Access required climbing narrow footholds carved into the rock or scaling ladders that could be pulled up at night. The structures themselves were masterclasses in pest-proofing. Walls built with flat stones fitted so tightly that not even a grain could slip through. Floors elevated on pebble-filled foundations to block moisture, and doorways sealed with fitted stone slabs or woven grass mats impregnated with bitter herbs rodents avoided. At Mesa Verde's Cliff Palace, archaeologists found granaries still containing 800-year-old maize kernels, their viability preserved by the constant 55-degree temperatures found at that elevation, a natural refrigeration system the pueblones discovered centuries before thermodynamics had a name. The construction process reveals just how communal this effort was. Hauling hundreds of pounds of sandstone blocks up sheer cliffs wasn't a solo endeavor. It required teams passing materials hand over hand along human chains, with elders directing placement and children carrying lighter loads of chinking mud. Some granaries show evidence of specialized labor, with certain masons consistently achieving tighter seams, suggesting apprentice systems where skills were honed over generations. The locations weren't random either. Granaries were often positioned near watchtowers or along routes to springs, turning food storage into both an early warning system and a way to monitor community resources. Modern archaeologists using 3D mapping have uncovered even subtler brilliance. At Canyon de Chelly, granaries cluster in storage neighborhoods where the rock's acoustic properties amplified sounds, a built-in security feature that let guards hear intruders scrambling below. Others in Choco Canyon align with solar markers, their shadows acting as agricultural calendars signaling when to plant or harvest. The pueblones even developed different granary designs for various crops, taller, narrower chambers for corn to allow air circulation, squatter rooms for squash with plastered walls to retain humidity. Today, these gravity-defying pantries offer lessons that transcend history. Seed banks in Norway's Svalbard and Colorado's National Center for Genetic Resources now use elevation and natural insulation principles inspired by Puebloan designs. Backpackers in the Southwest still employ the ancient trick of hanging food sacks from cliffs to deter bears, proving that sometimes the oldest solutions remain the smartest. When you stand beneath one of these high-altitude larders, you're not just looking at a storage room, you're seeing a civilization that outsmarted hunger by thinking vertically, turning sheer rock faces into the ultimate safe deposit boxes for survival. Deep in the rainforests of Meghalaya, where monsoon rains turn rivers into roaring torrents, the Khasi people perfected an architectural marvel that defies modern engineering: bridges that grow stronger with time. Unlike steel beams that rust or concrete that cracks, these living root bridges are alive, their tangled strands of rubber tree roots thickening into sturdy walkways high above the water. The process begins with patience and vision. A planter selects a young Ficus elastica tree on one riverbank, then guides its pliable aerial roots across the chasm using hollowed-out betel nut trunks as temporary scaffolds. Years pass as the roots creep forward inch by inch, eventually reaching the opposite bank where they're carefully woven into the soil. What emerges decades later isn't just a crossing, it's a symbiotic masterpiece where human intention and arboreal growth become inseparable. The brilliance of these living bridges lies in their dynamic strength. Traditional bridges degrade under stress, but root bridges respond to pressure by growing thicker at stress points, like a muscle strengthening with exercise. Some spans in Cherrapunji have borne daily foot traffic for over 500 years, their roots now as thick as a person's torso, interlocked in a lattice more resilient than any human-made mesh. During floods that sweep away modern steel structures, the roots simply bend with the current, their flexibility preventing catastrophic failure. Local guides point out bridges with peculiar bulges, places where generations of villagers added stones to weight the roots downward, encouraging them to thicken precisely where extra support was needed. This wasn't just construction, it was a conversation with biology. What's often overlooked is the sophisticated ecological knowledge embedded in this practice. The Khasi didn't choose ficus trees randomly. They understood this species produces secondary roots that fuse when they touch, creating natural reinforcement. They planted companion species like areca palms whose fallen leaves enriched the soil and timed maintenance to the tree's growth cycles. The bridges became ecosystems unto themselves, hosting orchids, ferns, and even beehives that provided additional food sources. Some double-decker bridges feature separate walkways for humans and livestock, their designs evolving from centuries of observing animal behavior and erosion patterns. The social dimension was equally remarkable. Maintaining a living bridge became a multi-generational responsibility, with families passing down stewardship like an heirloom. Children learned to gently train new roots while elders shared stories about which techniques worked during record monsoons. Villages held festivals when roots finally touched the far bank, celebrating not just the utility of the crossing but the living connection it represented between communities. Unlike modern infrastructure projects that divide landscapes, these bridges literally grew relationships, their roots intertwining with the cultural fabric as deeply as with the riverbanks. Today, engineers study these arboreal wonders for lessons in sustainable design. MIT researchers have modeled their load distribution for next-gen biomimetic architecture, while environmentalists champion them as blueprints for climate-resilient infrastructure. The longest-known example, the Umshang double-decker bridge, now draws visitors from across the globe, not as a museum piece but as a functioning testament to slow, thoughtful building. When you walk across one of these living bridges, you're not just crossing a river, You're stepping into a philosophy where time isn't an obstacle but an ally, and where the best structures aren't imposed upon nature, but emerge from patient collaboration with it. Thatch roofs glowing golden under the sun hid a brilliant secret in their smoky shadows, a preservation technique so effective it could double a roof's lifespan without a single chemical. Picture a thatcher kneeling inside a freshly completed roof, carefully tending a smoldering fire of damp straw or aromatic herbs. This wasn't just for warmth, it was a slow alchemy transforming the thatch itself. As the smoke curled upward through the dense layers, tar like creosote condensed on the reeds, coating each stem in a protective glaze that repelled moisture, fungi, and most importantly, the ravenous insects that could reduce untreated thatch to dust in a few seasons. The magic lay in the details of the smoking process. Builders didn't want roaring flames, just enough heat to produce a cool, dense smoke that could penetrate every crevice. In England's West Country, they used smoke bays, special chambers beneath the roof where fires burned for days at a time, while in Scandinavia, juniper branches added antiseptic properties to the smoke. The creosote acted like nature's pressure treatment, its phenolic compounds making the reeds indigestible to thatch pests like the dreaded thatch moth, whose larvae could skeletonize a roof from the inside out. Remarkably, this treatment also made the roofs more fire-resistant. The same tarry deposits that repelled water helped smother stray sparks before they could take hold. What's fascinating is how regionally specific this practice became. Japanese thatchers employed smoldering rice straw, whose silica-rich smoke left behind a glassy coating, while Pacific Islanders used coconut husks to produce smoke rich in natural potassium salts that deterred mold. In the Scottish Highlands, peat fires lent their distinctive smoky perfume while depositing acidic compounds that hardened the thatch like laminate. Some European manor houses even incorporated permanent smoke channels in their roof designs, narrow flues that allowed slow smoking to continue periodically for decades. The social ritual around smoke treatment was just as layered as the thatch itself. In Ireland's thatching communities, the first smoking of a new roof often coincided with harvest festivals, blending practical maintenance with celebration. Children would be tasked with gathering specific herbs, lavender for fragrance, thyme for insect repellency, while elders monitored the fire's temperature by observing the smoke's color and density. The knowledge passed down wasn't just technical, it was sensory. A master thatcher could tell by the smell when the creosote had fully saturated the reeds, or by the sound, a faint crackling, that signaled the process was complete. Modern science has since confirmed what tradition long understood. Microscopic analysis of centuries-old thatch from preserved cottages shows creosote penetrating up to 4 inches deep, forming a gradient of protection that renewed itself slightly with each rain. Laboratory tests comparing smoked and unsmoked reed samples found the treated thatch resisted microbial decay 3 times longer. Today, a handful of heritage thatchers still practice smoke treatment, not as historical reenactment, but as a genuinely effective alternative to synthetic pesticides and preservatives. When you see an ancient thatched roof still intact after 100 winters, you're not just looking at craftsmanship, you're seeing the legacy of generations who understood that sometimes the best preservative doesn't come from a factory, but from the patient dance of fire and smoke through 1,000 hand-laid reeds. From igloos to Adobe, from coral bricks to living root bridges, what unites these ancient building traditions isn't just ingenuity, it's humility. Our ancestors didn't conquer their environments with brute force. They listened, learned, and collaborated with the materials nature offered. That Viking builder carefully peeling birch bark for a turf roof wasn't just gathering supplies, he was having a conversation with the forest. The Puebloan mason fitting stones without mortar wasn't just stacking rocks, he was decoding the language of gravity and balance. These weren't primitive methods, they were masterclasses in working within limits, transforming constraints into creativity. There's profound wisdom in these time-tested techniques that our modern world is only beginning to rediscover. As climate change reshapes our landscapes, engineers now study how adobe walls regulate temperature without electricity, how bamboo structures flex through earthquakes, and how thatch roofs manage moisture without synthetic membranes. The irony is striking. The very technologies we once dismissed as outdated are now guiding cutting-edge sustainable design. A Greenlandic igloo's passive heating principles inspire Arctic research stations, while the self-repairing properties of Mayan lime mortar inform modern concrete alternatives. But beyond their practical lessons, these ancient structures whisper something deeper about our relationship with the planet. The Khasi root bridges teach us that the strongest foundations grow slowly through care and connection. The marsh Arabs' reed islands remind us that homes can float lightly on the earth rather than weighing it down. Every coral block in Zanzibar, every sod brick on the prairie, every paperbark shelter in Australia carries this same message. True resilience comes not from dominating nature, but from understanding our place within its systems. Next time you pass a historic building, whether it's a stone cottage or a timber-framed barn, pause for a moment. Run your hand along its walls and feel the echoes of forgotten skills. That uneven surface, that's the mark of a hand tool. That subtle curve, that's geometry learned through trial and error over generations. These structures aren't just artifacts, they're living libraries of sustainable wisdom, waiting for us to rediscover their pages. If these age-old innovations inspire you as much as they inspire us, share your thoughts below. Have you encountered ancient building methods that left you in awe? Maybe you've visited a cliff dwelling or slept under a thatched roof. Let's keep the conversation going. And if you're hungry for more journeys into humanity's ingenious past, hit that subscribe button. We're just getting started. After all, the future of building might just be hidden in the quiet patience of those who built without blueprints, proving that sometimes the oldest solutions are the most revolutionary.